Hello, it's Keith here, and this is lesson 60 of the platform-specific series of my 650 assembly programming tutorials, and we're looking at Mintile again on the Commodore 64. Mintile is, of course, my multi-platform tilemap code. It's got a multi-platform module that works on all 6502 systems, and it's got a platform-specific part just to do the tile code on the Commodore 64, and you can see the example running here. We've got two Chibico characters, that's my mascot, and you can see they can move around the screen, and if we press the fire button, they can X-flip. Mintile supports X-flip, it does not support Y-flip. I'm working on a more advanced version called Maxtile, which supports both. Now, one interesting thing about Mintile is it doesn't use a double buffer, it only uses a single buffer because not all systems can provide double buffering, so that reduces the amount of memory it requires, and it also means some changes to the way the code actually works. So what we're going to do today is we're going to take a look at the Commodore 64 version. Let's go over and let's look at the code. So this is the file we're going to be looking at today, C64 Mintile. So that's what we've got here, and we're not going to look at the code that's not specifically related to the tilemap. So we're not going to look at things like reading in the joystick or moving objects around the screen, because that's just processing data from the joystick and moving variables around. What we're going to look at is the new code related to the tilemap. Now, when we want to draw graphics to the screen, you can see the example we're running today has a tilemap in the background, and it also has these characters moving, and the characters I will refer to as software sprites. They're actually drawn with the tilemap code. It's the same code doing both. The reason for that is less code to port to more systems. I've ported Mintile to about 24 or more systems, and the less code you have to port, the more likely you are to finish the project. So by using the tilemap code to draw simple, crude sprites as well, we can port our game to more systems more quickly, and that's something I would strongly recommend. Try and funnel as many of your functions through the same platform-specific module if possible. Use the tilemap code for your fonts, for example, as well. If you can do everything with one piece of graphics routine, you will save yourself a lot of time. Now, when we're drawing the background, we draw the entire tilemap in one go. Now, the screen base is being configured as memory address 6020 in this case. So that is the center of the screen. Now, what we are actually doing is we're not using the full area of the screen. Mintile is designed to work at 32 by 24, so we've actually got it centered there, so we're not using the full 40 byte wide screen, we're actually centering it, and that's why we're offsetting by 20 there. So our memory base is 6020 here, and that is the start of our screen memory. Now, that's for when we're drawing the entire tilemap, but when we're drawing the sprites, we need to actually calculate the offset that the sprite needs to be drawn, and we've got a function called getScreenPos to do that. Now, all of my tutorials these days work in coordinates that are logical units, and that's one logical unit is 2 pixels. This is far more convenient for working on the kind of resolutions the systems I work with have, and it works well with single byte coordinates. So that's what we're using today. Now, one logical unit might be 2 pixels, but one tile is 8 pixels, so that's 4 logical units. Now, on the Commodore 64, because we're working in 4-color mode here, we're actually using tiles of 4 by 8, although this will actually work in 2-color mode as well on this example. So if we just run it again here, you can see now we've not got the right graphics, but we can actually work this in 2-color mode, in which mode the tiles are actually 8 by 8 pixels, but in 4-color mode, to keep the screen size the same, we're actually using 4 pixel wide tiles, 4 by 8 effectively. Now, when it comes to calculating the coordinates for the screen, we're basically rounding the Y coordinates into whole tiles. Now, this is because it makes it far easier to work with the screen memory layout of the Commodore 64 if we do that. So you can see here, we're effectively rounding here our tile coordinates to an entire tile here. And what we're doing here is we're calculating the VRAM destination and adding the base and the offset, skipping 4 blocks effectively, moving us to the center of the screen there. So that is that's calculating the screen coordinates for the sprites, but the tiles actually use this the tilemap actually uses this defined version here. Now, when it comes to drawing an object to the screen, be it the entire screen or just one of the sprites, we have the multi-platform code that does most of the work, and it breaks the entire object up into strips, horizontal strips, and it draws these one at a time to build up the object. So what happens is the multi-platform code will call this doStrip routine, and that will draw one entire strip and then return, and then the calling routine will run again and again to build up the object we're trying to do. Now, doStrip will draw an horizontally flipped strip. We have a version called doStrip reverse, which does an X-flipped version, which we'll look at in just a moment. So how does this work? Well, basically what we're going to do is we're going to read in from the 0-page entries marked as BCS. Now this is a 16-bit pair. BC is a representation of the Z80 register that does the same job on the Z80 version, S being shadow registers. So you don't need to know what BCS really means. It's just a 16-bit pair with a name. That's all it is. So this is the tilemap data, the tilemap that we're drawing, and each tile is a single byte in the tilemap, although we can use different tilemaps for the background and the sprites. The sprites have their own miniature tilemaps, you see. You can actually see those somewhere. Where are they? Here you go. Here's the miniature tilemap for the Chibico sprite, and here's the background tilemap. So that's what we're actually drawing. Now, a value of 0 in the tilemap has a special purpose. In the case of the background, because we've got no double buffer, the background is actually a cache of changes. And so 0 in there means no change, do nothing. A value other than 0 is the new tile number. In the sprites, it's actually transparent. So parts of the sprite, if you look around the feet, if the character would stop moving around so much, you can see parts of the feet have no tiles drawn, and that is 0, and that's transparent. So if we've got an empty tile 0, we're skipping the next part of the code. But if we've not got an empty tile, we're checking what we want to do. Now, we could be running them from cartridge memory here, so we're checking the value in memory tile clear. I use self-modifying code on some systems, but I'm tending to use a RAM variable instead here, just because self-modifying code doesn't work on cartridges. And so here we're checking if the clear flag is set, and if it is, we're writing a 0 to the tilemap here. The X register is 0 throughout this routine, so it's always 0. Now what we're going to do next is we're going to take the tile number we read in, we stored into Y there, and we're getting it back here, and we're going to effectively multiply that by 8, because there's 8 bytes per tile, because our tiles are either 4 pixels wide in 4-color mode or 8 pixels wide in 2-color mode, but either way that's 8 bytes per tile. So we're multiplying it up there, and we're adding this to DS and DS here, the 16-bit pair. And this is the offset within the memory for the start of our pattern data, the graphics that we actually want to transfer to the screen. Okay, so we've now got our source data, and our VRAM destination is in HL. And so what we're going to do is we're going to read in a byte from this source pattern data and write it to the screen, and we're going to increment Y. So we're using Y as an offset for both the source and destination here, and because of the way the Commodore 64 screen works, because vertical lines go down the screen for 8 bytes and then jump back up. That's why we're aligning to an 8-pixel boundary for our tile drawing. It makes this code much easier. If it was working in any coordinate, we'd have to be more thorough and check our coordinates after each one and make sure we were updating the VRAM address to move to the next sort of tile block if we'd gone over that boundary. But because we are limited to an 8-pixel boundary here, an 8-pixel limit here, we can just repeatedly inc Y 8 times to move through all of the 8 bytes for our tile. Once we've done all 8 bytes, we're then going to increment the source BC tilemap address, and we're also going to add 8 to our VRAM destination. 8 bytes in memory go down 8 times, and then the 9th byte jumps back up here. So by adding 8 here, we're effectively moving across one tile. So that's updating the HL pair to move across the screen for the next tile. We're then using IYL as a counter for the number of tiles to do in this job, and we're repeating until we've done. So that's how we're drawing either our little sprites or our entire tilemap unflipped. What about if they're X-flipped? Well, we're going to have to, we could have a second copy of all the pattern data, but that's far too wasteful. We could do real-time calculate the shifted bits, but that's very slow. So what we're going to do is we're going to use a lookup table. What we've got is we've got a lookup table generated. If we look at here, we've got this flip LUT. If we find the definition, you can see this is aligned on an 8-bit boundary, and this means that the flip LUT lookup table will start with the bottom byte of the HL memory address as a 0, so it will go from 0 to 255 at some memory address. We don't know what the top byte will be, but we know that the bottom byte will start at 0, and that is important for the way we're using this. What we're going to do is we're going to define all 256 possible source bytes and calculate their flipped equivalents. Now we're going to use the bottom byte of the 16-bit lookup table address as the source byte, and the destination byte will be written to that address. So we're going to use Y as an offset here, and we're loading HL with the flip LUT address, and then we're transferring Y, the byte that we want to convert, and then we're doing a bit shift here of 4 color values, the 4 pixels within the byte here. We're shifting them around and we're flipping them horizontally effectively, and this is the 2 color version, which is just a combination of left and right rotates. We're then storing the flipped value back in. We're incrementing y, going from 0 to 255. When that wraps around back to 0, we've done our lookup table, and we simply carry on, and we've finished our lookup table. Now that's how we build the lookup table. How do we use it? Well, it's pretty straightforward. So basically, we've got very similar code here. We are loading the BC pair in the 0 page with the address of the lookup table. We're only loading the B part here with the top byte of the lookup table. We load the C part with the byte we want to flip. So we're loading in the source pattern data from HLS here. We're saving that into the C part of the BC pair. We're then loading in from the BC pair there. And because we've set the C part to the byte we want to convert, we're actually loading in the flipped equivalent from the lookup table, and then we just write that straight to the screen. So that's how we're X-flipping our bitmap data. It's very quick relative to any other kind of thing because we've already done the calculation work. And this allows us basically to do the shift very efficiently, at least a lot more efficiently than the other options. And basically the other code is pretty much the same. We're still moving across the screen from left to right, but we're working backwards through the tilemap here. So we're moving backwards in reverse for it in our source tilemap, but we actually process the reading in the data in exactly the same way and calculate the pattern data offset in exactly the same way. And that is how we are doing our example there. So this is Mintail. This is a simple example. We're going to be doing another one later on called Maxtile, which is far more advanced. It supports Y flip, it supports XY flip, it supports simple transparency and a few other things. That's going to be coming later, so if you want to see that, please stick around. Anyway, I hope you've enjoyed what you've seen today. Thanks for watching, and goodbye.